next, let's see how we can extend this idea of eligibility traces to work with function approximation. So with function approximation, the eligibility trace is not a vector over the entire state space. Again, we can't store a specific value for each state in our state space. Instead, the eligibility trace is a vector with a dimensionality that is the number of tunable parameters, right? So we'll have an eligibility score for each tunable parameter in our function approximator, okay? So it has the same number of components as the tunable parameter vector, okay? So the tunable parameters vectors can be thought of a long-term memory. We update it over episodes, and we're trying to massage the function approximator into the correct position. And this will be accumulating and tuned over the lifetime of the system. But on the other hand, the eligibility traces is a short-term memory, typically lasting less time than the length of an episode. Okay, it decays over time. At each time step, the eligibility vector is updated with the addition of the gradient of the approximation function. Okay, so we update the eligibility vector with some decaying factor of gradients. So each time we see a gradient at each time step, we add it to the eligibility vector. So the eligibility traces, the eligibility score represent magnitude of gradients for each tunable parameters, and these are decayed over time, okay, or decayed over time steps. So the eligibility trace vector keeps track of which tunable parameter contributed positively or negatively to recent state valuation by storing the magnitude of the impact, right? This is exactly the gradient. Well, recent is defined in terms of lambda and gamma. So the trace in the eligibility traces, right, for the approximation case, it indicates the eligibility of each component of the weight vector for undergoing learning changes should a reinforcing event occur. The reinforcing event we are concerned with are the moment-by-moment one-step TD errors. Okay, we're still using the TD error multiplied by the gradient of our function approximator to guide the eligibility traces. The tunable parameter vector is updated on each step proportional to the scalar TD error and the vector of eligibility traces. So exactly what I just said, right? And these gradients, they diminish over time. Okay, so we keep the eligibility based on these gradients that we compute on a moment-to-moment manner. So this is the pseudocode for semi-gradient TD lambda for estimating the state values for given a specific policy, right? And so here we see the eligibility for, or the eligibility trace, the eligibility vector represents the eligibility for any theta I, for any tunable parameter, and this is determined by the partial derivative of theta I. It can be positive or negative, and that partial derivative decays over time. So in practice what happens is that the first update is based on the gradient at the current time step, right after a specific state st is visited at step t. So we set the eligibility at time step t to be exactly the gradient, and we update all of our tunable parameters based on this gradient, or this gradient multiplied by the TD error, represented here as small delta. And the next updates are based on, following updates will also be based on the gradient that we computed at time step t, but with diminishing eligibility. Okay, so we update the eligibility at each time step by diminishing the previous eligibility and adding the new gradient at the current time step, right? And so again, you'll have a exponentially diminishing eligibility for previously seen gradients. So you can think of it as something like at time step 4, the gradient that we computed at time step 1 has a very low weight, at time step 2 has a higher weight, 3 has a higher weight, and 4 has the highest weight. Okay, if we are at time step 4. So meaning that we just keep the eligibilities for the gradients and not for specific states.